This paper is called The Rational Agent Benchmark for Data Visualization. I'm Yifan Wu, a fourth-year PhD student at Northwestern University. This is my joint work with Ziyang, Michalis, Mamakos, Jason Hartline, and Jessica Hullman. So visualization researchers may wonder about the following question. What is the value of a visualization? Suppose there is a research experiment that's published in a paper, and the research question is, which visualization is most helpful for people to understand a weather forecast? These are four different visualization strategies for comparison, only displaying the mean with confidence interval, the mean with gradient, hypothetical temperature outcome plots. So participants are asked to complete a task to evaluate their understanding of the visualization. So after they see a weather forecast visualization, they reason about whether the weather is going to be freezing, and they decide whether to salt a parking lot. So the stimuli is a visualization display that's one of these four types. And usually researchers report the result as a ranking of the average performance across these four different visualization types. Um, yes, we have the result, we have the ranking, we have the data from experiment, but how do we know how much we have learned? There are a lot of ambiguities. Like people may wonder, how hard is the weather forecasting task? So only when they know how hard it is, they know how to interpret the unit of that difference observed in the experiment. And are participants incentivized if people believe they are going to be incentivized by money? And what's the impact of information asymmetry, like showing the mean of the temperature is not the same as showing the mean plus confidence interval? And what are sources of behavioral errors? Are participants biased towards one action in the experiment? And a lot more. So our contribution is we provide a framework to quantify the value of visualization given a visualization experiment design. So our framework enables us to pre-experimentally avoid issues beforehand. For example, by analyzing the information asymmetry, we know pre-experimentally that these visualizations may have a different performance. And also post-experimentally, our framework help people understand the data. For example, are people biased or it's simply the visualization is bad? So our framework takes a real-world experiment, which may be an experiment that's published in a paper with behavioral agents. And we set up a rational agent in ideal world for comparison with the behavioral agent. So our rational agent knows experimental setup and makes the optimal decision to maximize expected utility. So let's imagine we pick the weather forecasting visualization paper. So our framework analyzes an experiment. So the input is simply an experiment that's reported in the visualization paper. So in the weather forecasting paper, the stimuli is one of these four types. And the results is a ranking between them with mean with gradient maybe performing the best and showing only the mean is the worst. The question is, what do we learn? Our framework answered this question, and I'm going to illustrate by applying this to the weather forecasting example. So our framework is a decision theoretic framework. Firstly, we want to apply our framework. We firstly want to identify the decision task that participants are faced in the experiment. So there are 5 key elements of the decision task. The first one is the payoff relevant state that participants care about and directly influence their payoff. So the payoff relevant state here in the weather forecasting example is a binary one, which is whether the weather is freezing or not freezing. And then the data generating model, which is how the researchers generate the stimuli. And here, this is how this freezing payoff relevant state is generated, which is determined by another fine-grained state, which is the daily low temperature, drawn from a normal distribution. With this normal distribution, this has a mean fixed at 5 and a standard deviation that's drawn uniformly from 4 levels, 2, 3, 4, 5. And this is equivalent to saying the probability of freezing in any random trial is drawn uniformly from these 4 levels in the table. And then the agent's action space. So here in the weather forecasting example, the agent picks an action with from the space of sorting or not to sort. So we think of a visualization display as a signal that's correlated with the pair of relevant state. So since there is correlation, the agent is able to infer about the distribution of the pair of relevant state. So in the weather forecasting example, there are 4 types of visualization strategies. We think of each visualization strategy as an information structure that's a joint distribution over the state theta and the visualization display. For example, for mean is not varying with the pair of relevant states, the probability that generates them. So there's only one possible mean display that's shown to the agents in the experiment. So the joint distribution between the mean display and the pair of relevant state only has one probability that's displayed in this table, which is around 0.08. But for other visualization strategies, knowing them is the same as knowing the distribution where the temperature is drawn, and also the same as knowing the standard deviation sigma. So here this table shows the joint distribution between the sigma, the display for sigma, and the state taking values of freezing or not freezing, showing the joint distribution. And then there is a scoring rule or a payoff rule that's specifying what action is good under what payoff relevant state. For example, in the weather forecasting task, the agents are told it's good when they choose not to salt the parking lot and the weather is not freezing, or they choose to salt the parking lot and the weather is freezing. They get a payoff that's 0, which is the highest possible. And they get a punishment of negative 100 when they choose not to salt the parking lot and the weather is freezing. They get to pay their effort of salting when they choose to salt and the weather is not freezing. This is the scoring rule. So for the scoring rule, it has 2 usages. The first one is to incentivize people to take a better action. And then people can also use it, experimenter can also use it for evaluation after they got the data from experiment. So experimenter can actually use different scoring rules for incentivization and evaluation. For example, if they don't believe people can be incentivized by money, they can simply use flat payment, which is rewarding people based on the number of tasks. And they can use another scoring rule for evaluation post-experimentally. For example, they can commonly use the quadratic scoring rule, which scores people on the quadratic difference between the action and the payoff relevant state. These are the 5 key elements of a decision task. And this setup can be defined for all visualization studies as long as 2 conditions are satisfied. First one, the pair of relevant states are differing in different trials. So one counterexample is the exact same data is used for visualization. This is saying a single visualization is used as the stimuli in the experiment. So there is no uncertainty about the state in decision problem. And another condition is there is a best response that's mathematically best. One counterexample is people are asked to report something subjective, like emotions. So under our framework, we can analyze the value of visualization both pre-experimentally and post-experimentally. First, the pre-experimental part. Pre-experimentally, we set up a rational agent under the decision problem. So we provide benchmark by defining the rational agent's performance. So the rational agent goes through the experiment the same as behavioral agent, but she optimally processes the information in visualization and makes the best response action. When we are talking about best action, it's defined as expected payoff maximizer under Bayesian framework, which is the standard way to talk about rational behavior on the decision theoretic framework. So they start from a prior belief, they see the visualization, they update to a posterior belief using Bayes rule, and they take the best action given their posterior belief. And the best action is the expected utility maximizer. So for example, if they believe the probability of freezing is greater than 0.1, they should choose to salt the parking lot to get a better payoff from the experiment. Otherwise, they take not to sort. Here on the right, this shows the total range of score, which is the upper bound 0, the lower bound -100. Let's see what a rational agent would do with prior information. So the prior is when the rational agent never see the visualization, but they do a random trial. So this is the probability, the total probability of freezing in the experiment. So let's recall that the probability of freezing is drawn from 4 levels uniformly. In the experiment, the total probability is the average of the 4, which is around 0.08. Now we can define our baseline. The baseline is defined as the rational agent without visualization, that is only with prior information. So that's the expected score for rational agent without seeing visualization in any random trial in the experiment. So since the rational agent believes the probability of freezing is less than 0.1, she will take the action not to salt the parking lot, and she will get an expected score that's around -8. Notice that this score is obtainable for rational agent when she does not see the visualization. It's also obtainable by anyone that's choosing the fixed action, not sorting. And -8 is around here in the total scale. And then we have the baseline. We are able to talk about the upper bound. The upper bound, the visualization optimal, is different across visualizations. That's the rational agent seeing the visualization. After seeing the visualization, they have the posterior belief, which is probability of freezing, and this is equal to the prior belief is if the rational agent see the mean visualization, because mean is not varying with probability of freezing, so it's not informative. But they know the freezing probability in that trial for other visualization strategies, because other visualizations show the distribution of the temperature. So for mean, the upper bound is the same as the baseline because the mean is not informative. And for other visualizations, the upper bound is something that's improved around -5. So we define the rational benchmark as the best possible across visualization strategies. And it's something that's higher than the rational baseline. So from prior to posterior and best action to posterior, the rational agent gains something that's we call a value of information, which is around 2, the difference between the rational benchmark and the rational baseline. There is a difference in the upper bound. We call it information loss that's created by information asymmetry. That's information that's not in visualization display. For these 4 different visualization strategies, the mean visualization has an information loss that's 100% because for mean, the upper bound is the same as baseline and it's losing a 100% of the value of information between baseline and benchmark. So this is very bad. But for other visualization formats, they don't lose anything. So they have an upper bound that's the same as benchmark. We say the information loss is 0 for other visualization formats. So pre-experimentally, the experimenter can expect mean to behave badly compared to other visualization formats. So this is the pre-experimental value of information, and this can be calculated before the experiment, before any experiment is run, and this is the rational agent's gain. So pre-experimental analysis enable experimenter to get a sense of which scale they should compare to. For example, in the weather forecasting task, this scale is like only 2% of the total scale of the payoff, and this is very small. And also, they can analyze the impact of information loss on the average performance. Also, they can analyze, are people incentivized to read the visualization by analyzing the rational agent's gain in monetary reward. And then we are going to talk about post-experimental analysis with behavioral agents. So behavioral score is defined as an average payoff of a behavioral agent who see the visualization and takes action. So behavioral score is of course lower than the rational benchmark because by definition, the rational agent is doing the best to maximize expected utility. And this is the post-experimental value of information, which is the gain above rational baseline. When this gain is positive, like the behavioral agent is doing better than the baseline, we can say they're doing better than someone that's always taking the fixed action. So we say the behavioral agents are learning something from the visualization. So when we compare behavioral value to rational value, which is post-experimental value to pre-experimental value, we see there is a difference between them. And usually behavioral agent and this loss is created by different sources. So the first one is the information loss that's I talked about when that's created even before the experiment is run. And then the behavioral losses. If we compare behavioral agent to a rational agent, we know they may not receive perfect information in the visualization, and also they are not best responding to their information. So we quantify the losses induced by these two reasons by asking the following question. What would a rational agent do given the behavioral agent's information? We define a calibrated behavioral agent, who is a rational agent given the behavioral agent's information. So the calibrated behavioral score is defined as the average score of a rational agent who has the prior, who sees the behavioral action as a signal, and updates to the posterior according to the Bayes rule, and takes the best action to her posterior. So this is retrieving the information for the behavioral agents. And the calibrated score is between the behavioral score and the benchmark. So we are able to separate different losses. First one is the belief loss when the behavioral agents see the visualization. That's the information that are not perceived. So this is quantified by comparing the rational benchmark, which is when the rational agent uses perfectly the information in visualization, and the calibrated score, which is when the rational agent only uses behavioral information. So this value is called the belief loss, the loss induced by information not perceived. And then the optimization loss, which is when the behavioral agent not making the best action given their information after they see the visualization. And this is quantified by the difference between the calibrated score and the behavioral score. This score quantifies how much behavioral agent can be improved when they are acting like a rational agent. We apply our rational framework to two award-winning papers. The first one is the effect size judgment paper in VIS 2020. And the other one is the uncertainty display for transit decision making in CHI 2018. So these two papers are known for their rigorous experiment design, but by applying our framework, we still have new findings. Like our findings say, usually for these two papers, the baseline is always a good fraction of the benchmark, which is best possible achievable in the experiment, like over 80%. So, like in Fernandez et al., the 2018 paper, they claim that behavioral agents are able to achieve 85% of the benchmark. This is not a valid claim because they're not comparing with a baseline. And the baseline is able to achieve a good fraction of the benchmark. And also, the Fernandez paper also lack sufficient incentive for people to consult the visualization because the agents, for the rational agent, she is guaranteed a base payment. And the gain from visualization is only like a 5%, which is relatively small. And we also find this connection between elicited beliefs and decision tasks. For example, in the 2020 paper, the optimization loss for decision tasks is very low. This is showing people are actually understanding the decision task. But for belief tasks, it's very high. So this is saying due to their experiment design, people are somehow bad at or answering the belief questions, but not the same as the reason in their paper claimed to be biased. These are the implications of our framework. Without formalizing decision problems we care about and the value of visualization to problems, we don't know what we know, and this is the main takeaway. We have pre-experimental analysis where we analyze the scale for comparison by setup, baseline, and benchmark. We also analyze the impact of information asymmetry, and we can analyze the incentives given to the agent. Post-experimentally, we are able to separate behavioral losses into belief loss and optimization loss, and other implications are dependent on experiment design. Our framework is not only applicable to visualization experiments, but also another wide range of studies like data-driven interfaces and other applications.